Hi everyone! Do you know what is duplex steel? Are you familiar with the terms of pitting corrosion or crevice corrosion? If not, this video is definitely for you. Due to their unique properties, duplex materials are used in the most severe conditions like deep water installation, offshore technology, maritime application, oil and gas, and of course in the chemical industry. This is the first part of the video series about duplex stainless steel. The following videos will cover the metallurgical specialties, weldability aspects, and I plan in the last video to show you guys some real-life application. So let's start with the basics. In this video we will only focus on the basics. What is a duplex material without any deep dive in the metallurgy? What is PREN or pitting resist equivalent number? We are going to discuss what is pitting corrosion, and finally what is crevice corrosion. These are the fundamental terms in the duplex materials. Before we start, I like to introduce myself, who I am. My name is Tibor Kemény. I am the owner of Time Special Engineering, an engineering advisor company located in Shanghai. Time specializes in welding, metallurgy, and supporting power and chemical equipment manufacturing. I offer engineering support in project preparation phase, develop suppliers in China, and I follow manufacturing of special equipment. I'm a mechanical engineer with materials and design background, and since 2011 I'm a professional welding engineer. I've been working in manufacturing since 2006 and spent almost 12 years manufacturing cranes, offshore equipment, roller coasters, and turbine housings for hydropower plants. In the last 8 years, I've been in the front line of manufacturing pressurized equipment for oil and gas, chemical plants, and last but not least, equipment for power plants. I'm familiar with ED 2000, EN code, ESME Section 1, Section 2, Section 8, Division 1 and Division 2, and of course, because I'm in China, with the GB code. As a former quality manager, I also have a strong background in ISO 9001 and 3834 standards. Feel free to contact me with manufacturing, metallurgical, or welding related questions. After this short introduction, let's start with the first topic for today. What is duplex material? Duplex stainless steel is a unique microstructure containing 50% ferrite and 50% austenite. You can ask, but why do we need this material? To answer your question, let's take a look on the individual materials. Austenite has excellent corrosion resistance and high toughness. This high toughness makes them suitable for cryogenic application. Even liquid helium can be stored in a vessel made of austenitic steel. On the other hand, austenite suffers from stress corrosion crack in a high chloride environment, and its yield strength is quite low. This means two things. For a given load, we need more thickness, more material, and austenite is expensive. And the second conclusion, in a high chloride environment, like seawater, we can face with extensive corrosion damage. Now let's take a look on the ferrite materials. Ferrite materials are the opposite. They have high strength and low toughness. Reduced corrosion resistance in general, but particularly resistant to chloride stress corrosion crack. So the idea was, okay, let's mix the two materials and hopefully we would get an alloy that combines all the favorable properties. And this experiment was successful, and the typical microstructure can be seen on the right side of this slide. The white areas are the austenite and the brownish lines are the ferrite. I will present their development history in more detail in the following video. PREN has an essential meaning in the duplex world. This abbreviation stands for pitting resistance equivalent number, empirical equation to evaluate the pitting resistance of an individual alloy. As I mentioned, this is only an empirical equation. This is not a corrosion test. So if you have a special material or some welded connection in highly corrosive environment, please do a separate corrosion test. But let's go back for the PREN. As a thumb, we can say the higher the number, the higher the corrosion resistance. But again, this is only theoretical. We use this number in the same stainless steel family. It doesn't make any sense to calculate the PREN for nickel basis alloy and use it against any stainless steel materials. Where do we use this PREN? In the real world, we use two different types of PREN numbers for a given alloy. The first number represents the normal condition, which means you have a body, let's say in the seawater, and to have a seawater resistant material, we need a PREN number minimum 32. But again, this is for the normal case. And we have the second case, which is more realistic. This is the crevice corrosion. We have all the time some kind of crevice because of the design, or we have some welding defects, or we have some problem with joining two plates together with bolted connection. We always have some crevice, and this crevice is more severe. I'm going to show later in this video what's happening in the crevice corrosion. And just to explain the difference between the PREN numbers, for a crevice corrosion we need minimum 40. So this means this corrosion is more severe. So this is for the two different PREN numbers. PREN is also used to characterize duplex materials. Based on this number, we can make different groups within the duplex family. For example, we can call the lean duplex materials. I'm going to explain all these terms in the following video. A lean duplex material means we have an alloy where the PREN number is between 23 and 28. A standard duplex material is between 30 and 40. Super duplex materials have a PREN usually between 40 and 45. And materials with PREN number higher than 45 called hyper duplex material. So that's all about the PREN numbers. Now we know what PREN is. It's time to become familiar with the pitting corrosion. Pitting corrosion is a localized surface corrosion that starts on a small area, which first transforms into a cavity, and this cavity will grow inside the material. This mechanism has 3 steps. Step 1 is the depassivation. We need a small area where the protective layer is somehow damaged. Step 2, formation of a cavity at this depassivated area. And the step 3, we're going to have an anodic and cathodic reaction, and this is going to attack the passivation layer, and the passivation layer gets entirely dissolved. As a result, we're going to have a low pH value, and this pH value it's like an acid, and it's going to completely destroy the surrounding area. But before we take a look on the individual steps, let's discuss why this corrosion is so dangerous. First, the problem is the cavities are small. So usually the first 2 steps are unnoticed. So nobody see those cavities because they are so small. Or even if they're big, they are, let's say, inside a heat exchanger, and you can see this area. And secondly, as this cavity grows inside the material, the structural integrity decreases. And in case we have a highly loaded structural member, this can be a catastrophic event. To give you a better understanding on this type of corrosion, let's inspect the individual steps. For any corrosion system, we need the following 3 ingredients: damaged passive layer, a corrosive environment, and susceptible materials. The first step is the depassivation. This can happen if there are a small, tiny crack or scratch in the passive layer. In most cases, this is happening because of the material handling. I see this all the time. Or we have some surface contamination, like dust from carbon steel, or dust particles in water, droplets on the surface, stainless steel surface. Another possibility is to having some non-uniform loads. For example, we have a pressure vessel and we have internal pressure, which means we have some kind of strain, and this strain can be so high that this passive layer gets damaged, and between the 2 passive layers we're going to have a gap, and this gap is a free surface without any protection. So this can be also a critical point for any corrosion. The next thing what we need is corrosive environment. What is a corrosive environment? Let's say we have seawater or any fluid or gas contains high chloride or bromide, fluoride, for example. And the last one, we need susceptible materials. What are the susceptible materials? Austenitic stainless steel, it's typical one. That's the reason actually why do we need duplex materials. Seawater application. Aluminium, copper. So for seawater application we need special copper alloys, let's say Admiral brass or something, to be able to use in seawater application. Now we know the 3 ingredients. Let's go for the step 2. As the chloride ions attack the base material, a localized corrosion cell forms in the pit. The pit becomes the anode, and the surrounding area becomes the cathode. Anode material starts to lose electrons, which leads to metal ion formation. At the cathode, in the meantime, a reduction reaction starts in which oxygen reduction becomes dominant, and they attack alongside chloride ions the base material. As a side effect, because electrons from the pit goes to the surrounding area, and from the surrounding areas chloride and hydroxide ion goes to the pit, the pH value in the pit drops. This is basically a chemical procedure, and we can formulate equations for the anode side and for the cathode side, what's happening in the language of chemistry. Those are the equations. Those equations going to be the same at the pit, at the crevice corrosion too. In the case of cavity propagation, chloride and hydroxide ions are working together, and they dissolve more and more material, while the pH value in the pit drops. So this is what I wanted to highlight in this sketch. We have a bigger hole, and we have more and more chlorides and hydroxide ions in the pit, which means the pH value is lower. And when we reach the critical value, the rate of corrosion increases. And this is going to be a very serious problem, because if we have some highly loaded structural member, this can cause a catastrophic event. We can have a structural problem or rupture. And finally, let's take a closer look at the crevice corrosion. This is also a localized corrosion, and it is very similar to pitting corrosion. The only difference here is that we need at least 2 neighboring bodies, and of course between them a confined space. Even the formation mechanism is also identical to the previously described pitting corrosion. Step 1, we need a gap or crevice. This can be a bad design or some bad welding joint. In this crevice we need formation of a cavity. Again, anodic-cathodic reaction is going to dissolve the passive layer. And due to anodic and cathodic reaction, the passivation layer gets entirely dissolved. And as results, we have a low pH value again, and the corrosion rate at this point in the increases. Again, this is almost the same as the pitting corrosion was. To give you a better understanding on this type of corrosion, let's have a heat exchanger. We have hot steam and we want to condensate this hot steam with a heat exchanger, and we want to use as a coolant agent called seawater in the shell side. The green area represents recirculated water, while the pink shows the trapped seawater in the crevice. The flow in the shell side is actually disturbed because there is a tiny area in the tube sheet connection where we have trapped seawater. And this trapped seawater contains a lot of chloride ions and some oxygen. And this is going to be the problem at the step 2. As I mentioned before, we have in this trapped seawater some oxygen and a lot of chloride ions. To have a passive layer on a stainless steel surface, we always need oxygen. Stainless steel materials have a lot of chrome alloy inside. The chrome and oxygen creates this passivation layer which prevent corrosion protection. But to rebuild this corrosion protection layer, we need oxygen. And in this case, as the oxygen level depletes, this passive layer cannot be rebuilt in the pink area. And this is going to be the problem. Because in this case, the stainless steel surface, the stainless steel material is not corrosion resistant anymore. As the passivation layer starts to dissolve, we are going to have a galvanic connection again. And in this relation, the gap becomes the anode and the surrounding area becomes the cathode. Again, this is completely identical to pitting corrosion. And we can use the same equation to describe the chemistry. We have the anodic side and we have the cathodic reaction. Again, everything is the same as the pitting corrosion. The previously mentioned galvanic connection promotes corrosion because the negatively charged hydroxide and chloride ions are migrating from the cathode to the anode, and in the meantime from the anode the electrodes migrating to the cathode, and we have this loop, this corrosion loop. It's a self-sustaining system, and as a consequence of hydroxide and chloride ion migration, the pH level in the pit drops again and the passive layer gets entirely dissolved, as we saw at the pitting corrosion. Without the passive layer's protection, the corrosion speed accelerates. At this point, leakage in this heat exchanger is only a question of time. This leakage can occur either at the welded joint, if the chemical composition of the welded joint undermatches the base material, or we have the corrosion damage first at the tube, because the tube is usually thinner than the throat thickness of the welded joint. Usually we use the same throat thickness for the welding joint as the tube thickness, but if you have ever seen a microsection of a tube-to-tube sheet joint, you can see the welding joint, it's always bigger than the tube thickness. So 99%, if the filler material is matched for the base materials, the corrosion damage is going to be on the tube first. And of course, a leakage in many cases is a serious malfunction. And this requires an imminent action from the plant owner, because you have some kind of highly toxic materials, and this is going to be mixed with seawater in this case, or with normal water. This can be a serious problem. So that was my first video about Duplex. I hope you enjoyed the show, because the next video it's going to be more interesting. I'm going to talk about welding, weldability, microstructure, and this can be challenging. If I recall my education, it was a long time ago, but if I recall correctly, we had corrosion and stainless steel materials only for 3 hours. We discussed duplex material, stainless steel, ferritic material, martensitic materials, corrosion, nickel bases, dissimilar joints, blah 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 blah, only in 3 hours, which was not enough. So I'm going to talk only about duplex materials at least 2 hours. And then I'm going to cover stainless steel, I'm going to cover nickel basis materials, ferritic materials, dissimilar joints, overlay welding, corrosion arts, because I really like metallurgy and welding. So what you have to do, stay for the next. Bye.